Here is your turn, so please take a look, take a couple minutes to think this out, write it out. So how would you convert negative 15.375 into an IEEE standard 32-bit single precision binary number? The steps will always be the same no matter what problem you're solving. So taking a look, so I want to convert, well, we'll save the negative sign for later, but I want to convert 15.375 into pure binary. So the 15 is easy. That's an 8 plus a 4 plus a 2 plus a 1. So that's 15, 1, 1, 1, 1, dot. So then the right-hand side, you could use the formula from earlier, like 0.375 times 2 is 0.75, so the 0 gets the next slot. 0.75 times 2, 1.5, so the 1 gets the next slot. And then 0.5 times 2 equals 1.0, so 1 fills in the final spot, and that is a quarter plus an eighth, or 2/8 plus 1/8 to get me 3/8, 0.375. So step 1 complete, 1111.011. Step 2, so then just tacking on the times 2 to the 0th power. Step 3, shift over the decimal point. So I need to go three spaces over in order to make it a 1 dot something so that I get my scientific notation. So 1.111011 times 2 to the 3rd power gets me the end of step 3. The final steps just kind of tie it all together. Once I have that binary scientific notation and I have it down correctly, I'm ready to go. So step 4, taking a look at the sign bit. I know I'm dealing with a negative number, so the sign bit ends up being a 1. That's easy. Step 5, this bias term of that exponent, because that exponent is a 3. But things are different here, right? Or they're the same because we're dealing with a 32-bit component. So the bias, 8 bits of storage, 2 to the 8 minus 1 is 127. So again, I need to add 127 to my 3 value from E. So my exponent is equal to the bias plus E. 130 in binary is 100000010. Fair enough. And that's the value that now you can bring down into the exponent part for those 8 bits, 130 in binary. And then step 6 finishes up the whole deal, and it takes the fractional part, everything after the 1 dot, as part of the M value, and just jams it in, and you notice a whole ton of zeros being added to the end, because we only have 6 digits, so there's 17 zeros that fill in the gaps. So taking a look at this, there you go, 1 1 0 0 0 0 0 1 0, and then 1 1 1 0 1 1, and a whole ton of zeros. That is the binary representation in this IEEE format for the number 15, negative 15.375. So let's take a look at a smaller example. So in this case, this is an 8-bit floating point representation. This is not an IEEE standard per se, because that only exists for 32-bit, 64-bit, and 80-bit right now at least. So otherwise we can just do whatever we want. In this case, I want to set up 1 sign bit, 4 exponent bits, and 3 fractional bits. So no matter what, there's only 256 values, right, that can be represented as an 8-bit quantity. And of course, for the total number of infinity, an infinite number of values I'm trying to represent, 256 is not going to touch much of the number line at all. And then you wonder, if I'm using this format, well, what is the largest value? What is the value smallest to 0? And it's interesting, right? Maybe it is, maybe it isn't. Be like, what is this representation? What does it give me for values? So again, same algorithm, sign bits to sign bit. The exponent, the bias would be a 7 here if I was doing the math on it, trying to add. And then the last 3 bits would be set aside for fractions. So you don't get too much, right? If you're dealing with a fractional component, if I only got 3 digits, that's down to the eighth, because a half is the first digit, a quarter is the second, and an eighth. So you don't get much more past eighths when it comes to the precision of the values that this thing can store. Here are some of the numbers that are being represented by this format. Not all of them, because there's 256 of them. That would take a while and take up a lot of space, but the important ones are here. So of course 0 is a number that can be represented, and the smallest value using this format, if you run out the math, you get 1/512th, or negative 1/512th. So anything past that, you lose precision. So 0.00 2, right? That's kind of how things go there. The largest number that can be represented is positive or negative 240, 240 being the magnitude of the number. So it's interesting. Anything past that you can't represent in this format. And anything smaller than 1/512th cannot be represented. And most likely almost any number you choose is going to lose precision. Anything between 224 or 240, it has to cut down to one of those two numbers. So if I said, what's 230, it would probably pick 224, and I would lose 6 off the number I'm trying to represent. And as you would notice, the further away you get, the more the error term would bother the result I'm trying to achieve. One final example here, a 6-bit floating point representation. Again, it's not an IEEE standard because it's not one of the 3 big ones, but it's 6 bits, which means there's only 64 possible values that can be represented in this format. So yes, we're even more constricted before, and now the question is what representations, what numbers can be represented in binary when we're talking about decimal numbers. So same rules apply. The bias would, in this case, would be 3, since it'd be 2 squared minus 1. But all the other rules apply. We have 2 bits for fractional components, and we're not worried about exact values here. I just wanted to show you right here, basically how are those 64 numbers spread out. So we learned from this that positive 15 is the largest number, negative 15 is the smallest number, and notice that, how does the distribution go? A lot of those numbers are very close to 0, or, near the middle, near the origin of the number line. And as we spread out more and more and more, those numbers get further and further apart. This figure is a little more zoomed in toward the origin of the number line, but, what do you see here? You see so many of those 64 values are very close to the -1 to +1 region. And pretty much if you're using the standard, everything kind of applies that way, because the standard was set up so that the numbers that you would use the most, pretty much the numbers close to 0, relatively speaking, because you generally don't use hugely large numbers using these data formats. So it makes sense to kind of have the most precision near 0 or closer to 0 than off to positive or negative infinity. So that's a good thing to understand, that, if you need a large number or a very small number, the rules are different. You might need to use more arbitrary or different software packages to handle the representations of those numbers than the floating point representations that we have here using the IEEE standard. So maybe you don't care about any of these slides in this presentation. You're like, why do I care about any of this? Why do I care how these numbers are represented? This slide pretty much shows you why you care. How do I, how these numbers are represented in binary, and how do I use them if I'm using C++, Java, or you name the programming language, since this is the floating point, the double, and the long double are pretty much standard now across every programming language. So when I'm converting from one number system to another, one data type to another, that's where this all comes in. So if I'm in step 1 here, if I'm taking a double or a float, and I'm cutting it and turning it into an integer, what am I doing? First off, it takes a lot of clock cycles, as you could imagine. You've done the examples. How do we make that happen? There's got to be something that makes it work in hardware, and it takes a lot of clock cycles to do. But otherwise, if we were just looking at this mathematically, you just pretty much cut off that, the decimal point, because you're truncating off, because an integer is a whole number with no decimal point, so you're essentially doing that. And if you want to think of it mathematically, if you have a positive number, you're taking the floor function, and if you have a negative number, you're taking the ceiling function. You're basically just hacking off the decimal component and leaving the integer component behind. So then now from int to double, that is the one that actually always works, because every integer value, all 4 billion of those values, can be correctly represented in the double data format. So all 64 bits of storage, all 18 quintillion numbers that are represented in 64-bit, those 4 billion from the 32 bits are in there. So you wouldn't lose any precision, and this presuming that you're using 53 or less bits. And you're like, why? What is with this 53 bits? If you go back to that slide that shows you the representation of the 64-bit double data type, you would see that 53 bits are used for the fractional component. So it would make sense that you don't try to spread yourself outside of that, because at the end of the day, that is what's represented minus the exponent portion plus the sign bit. So then the final part here, what happens when I deal from int to float? And you can imagine integer is 32 bits, floating point is 32 bits. They're both trying to represent every number possible in different ways. Integer doesn't do any fraction, but float, of course, is supposed to do all fractions. So it's going to do its best, but you can guarantee that a lot more numbers are going to be cut off and hacked off than you would using the double data format. So I would say if you can help it, use int and double for everything you do, and pretty much a lot of languages do that, and it's up to you to reduce down and go, oh, I need a short or I need a byte, but understand that, you know, some of this can actually apply and kind of be a negative for you. So if at all possible, int and double forevermore, and only use float if you have to. Like gaming uses float for speed, but as you could tell, that actually could cause some issues if we're not paying attention to what we're trying to do. So if anything goes to show here that we are computer scientists, applied mathematicians, we're basically trying to take all of mathematics, make it work on a silicon chip. We have to take approximations of all of this to make it work. So we lose a lot of true mathematics in that process. So associative rule, gone. Distributive rule, gone. Probably commutative rule, probably gone too. These things go because if we lose precision on the mathematics, then the addition, subtraction, multiplication, and division, what you get if you do a plus b plus c, or a times b divided by c, those kind of things, the order of operations matter. In true mathematics, that doesn't happen. So you can imagine for us compilers, people writing compilers, people using programmers, using these compilers, people creating serious simulations, weather simulations, astronomical simulations, things that are at the quantum level. You could see that that's going to cause an issue. All these imperfections in the end results of the calculations can cause some huge problems, especially as the simulation drags on and on and on. So it's like it makes it difficult. So it's one of those things, if we're using those kind of things, we have to look at to see if the error terms are sufficient for what we're trying to accomplish, and if not, we pretty much have to develop or use other software libraries in order to get this job done, so the precision is to where we need it to be. So today we took a look at how we represent decimal numbers in binary. That's the most important portion of what everything was about today. We do have to understand the limitations of our data types, so that's a big portion too. But understanding, at least for the first exam, understanding how I take a decimal value and how do I convert it into to binary, that's important. But after the first exam, you made it through. Let the computer do the job. It can do it much quicker, of course, than we can. So coming into the end here, so if you have any questions, many of you have been emailing me questions before I even made this video, which is great. So hopefully this settles a few of those questions you've been having. But if not, email away, come into my office hours, come on, say hi some way. Let's get that question answered, and let's move on to the next videos. Thanks for sticking with it, and we'll see you next time.